Imagine standing on the surface of Mars without a pressure suit. You draw a breath. Your lungs fill with air that would have killed you just decades before, but now sustains you. The sky above stretches in shades of pale blue, tinged with rust at the horizon. Clouds drift overhead, delicate and temporary, carrying the promise of rain that falls not as frozen carbon dioxide, but as liquid water. In the distance, a lake reflects the amber light of late afternoon, its shores lined with patches of green, simple grasses and mosses perhaps, the first whispers of an ecosystem still learning how to breathe. This is the dream of a terraformed Mars, a second Earth sculpted from a cold, barren world. But how long would it truly take to transform the red planet into something we could walk upon freely, to reshape an entire world's climate, atmosphere and chemistry until it becomes a home? Tonight, we're not simply visiting Mars. We're asking one of humanity's most profound engineering questions. Could we actually terraform it? And if so, how many human lifetimes would such an undertaking require? The answers are far more complex and far more fascinating than most imagine. This isn't a question of centuries or even millennia. Depending on the methods we choose, we may be speaking of tens of thousands of years, or with certain bold approaches, perhaps only hundreds. The truth lives somewhere in the intersection of planetary science, orbital mechanics, atmospheric chemistry, and technologies we're only beginning to understand. Terraforming Mars is not a single grand gesture. It is a symphony of interventions, each building upon the last, warming the planet, thickening its atmosphere, melting its polar caps, protecting what we create from the solar wind, introducing life in stages, from microbes to forests, each generation slowly preparing the ground for the next. Some scientists propose massive orbital mirrors to concentrate sunlight. Others suggest nuclear solutions, deliberate and controlled. Still others imagine redirecting asteroids, importing the very building blocks of atmosphere from the outer solar system. Each approach carries its own timeline, its own costs, its own profound uncertainties. What makes this question so compelling is that we're no longer speaking purely in science fiction. NASA, SpaceX, and research institutions worldwide are actively studying Martian resources, atmospheric potential, and the physics of planetary transformation. We have rovers analyzing soil chemistry. We have satellites mapping subsurface ice. We understand Mars better now than we understood our own ocean floors just decades ago. The dream is becoming an engineering problem, and engineering problems, no matter how vast, eventually yield to human patience and ingenuity. Before we drift deeper into the methods and timelines, I'd like to ask something. Wherever you are right now, whether you're watching beneath city lights or starlight, drifting off to sleep, or just beginning your day, leave a comment below. Tell us where you're watching from and what time it is in your part of the world. There's something beautiful about knowing that across this one planet we all share, curiosity unites us in the quiet hours, in the wondering about worlds beyond our own. Now, let us begin our journey, not with assumptions, but with understanding. To grasp how long terraforming would take, we must first see Mars as it truly is today, stripped of romanticism and fiction, standing cold and patient beneath a sky waiting for transformation. Before we can dream of transforming Mars into a second Earth, we must first understand what Mars truly is, not the Mars of science fiction, painted red and hospitable in our imaginations, but the Mars that exists now, suspended in the cold darkness beyond Earth's orbit, a world that is simultaneously familiar and utterly alien. To terraform Mars, we must begin with reality, And reality on Mars is harsh, unforgiving, and profoundly different from anything we experience on our home world. Stand on the surface of Mars today, and you would find yourself on a planet that whispers of what it once was. The Martian atmosphere is thin, ghostly, barely there at all. Its pressure measures less than 1% of Earth's atmosphere at sea level, equivalent to standing at an altitude of 100,000 feet above our planet. To breathe this atmosphere would be impossible, not just because of the pressure, but because of what it contains. 95% carbon dioxide, with traces of nitrogen, argon, and oxygen so sparse they might as well not exist. This is an atmosphere that cannot sustain liquid water on the surface, cannot carry sound more than a few dozen feet, and cannot protect anything below from the relentless bombardment of cosmic radiation. The temperature extremes on Mars tell their own story of a world without the blanket of a thick atmosphere. At the equator on a summer afternoon, temperatures might climb to a relatively pleasant 70 degrees Fahrenheit, warm enough that if pressure and oxygen were not issues, a human might stand comfortably in shirt sleeves. But this warmth is fleeting, a brief moment before the sun sets and the thin atmosphere fails to hold any heat. Within hours, temperatures plummet to minus 100 degrees Fahrenheit or colder. At the poles during winter, thermometers would register minus 195 degrees Fahrenheit, cold enough that carbon dioxide itself freezes out of the atmosphere and falls as snow, creating seasonal polar caps of dry ice layered atop water ice that never melts. Radiation on Mars is not just a concern, it is a constant, invisible threat. Without a protective magnetosphere, and with only a whisper of atmosphere, the surface is exposed to solar radiation and galactic cosmic rays at levels that would be lethal to humans over time. A year on the Martian surface would expose an astronaut to radiation equivalent to receiving a full-body CT scan every 5 or 6 days. This is not an environment that forgives biological life. It is an environment that must be fundamentally altered before life, as we know it, could persist, without constant technological protection. And yet Mars holds secrets that give us hope. Beneath its rusty surface lies water, vast quantities of it, locked in ice. The polar caps contain enough frozen water that if melted, it could cover the entire planet in an ocean several feet deep. Ground-penetrating radar has revealed massive ice deposits at mid-latitudes, buried beneath layers of dust and regolith. Some craters in the northern plains may contain glaciers concealed under protective blankets of debris. Water is not absent from Mars. It is simply waiting, frozen in time, preserved in a state that tells us Mars was not always this way. The gravity of Mars presents another fundamental challenge that cannot be engineered away. At just 38% of Earth's gravity, Mars tugs at objects and people with a gentleness that seems almost weightless by comparison. A person weighing 180 pounds on Earth would weigh merely 68 pounds on Mars. While this might seem appealing at first, the long-term biological implications are profound and largely unknown. Would human bones weaken? Would cardiovascular systems adapt or deteriorate? Would children born on Mars develop differently, their bodies shaped by a gravity that is neither Earth nor the weightlessness of space, but something in between? These questions remain unanswered, waiting for the first long-term inhabitants to provide the data. To understand why Mars is the way it is, we must look back into deep time, to an era when Mars was not a frozen desert, but a world of flowing water and perhaps even rain. Scientists believe that billions of years ago, Mars possessed a thicker atmosphere, one capable of sustaining liquid water on its surface. Evidence of ancient river valleys, lake beds, and even a possible northern ocean carved into the Martian crust tells us that water once flowed freely across this world. But something changed. Something stripped Mars of its atmospheric protection and transformed it into the cold, dry planet we see today. The culprit was the loss of Mars's magnetosphere. Earth's magnetic field is generated by the churning of molten iron in its outer core, creating an invisible shield that extends far into space, deflecting the solar wind and protecting our atmosphere from being stripped away. Mars, being smaller and cooling more rapidly than Earth, saw its internal dynamo shut down approximately 4 billion years ago. Without a magnetic field to deflect the solar wind, the charged particles from the Sun began to slowly but relentlessly strip away the Martian atmosphere, molecule by molecule, ion by ion, across billions of years. What remains is a planetary skeleton, the remnants of an atmosphere that was once substantial enough to support surface water and perhaps even microbial life. This magnetosphere problem is not simply a historical curiosity. It is perhaps the greatest obstacle to terraforming Mars. Even if we could somehow thicken the atmosphere, warm the planet, and create conditions suitable for life, the solar wind would continue its patient work of erosion. Without a magnetic shield, any atmosphere we create would begin to leak away into space, though admittedly over timescales of millions of years. Some scientists argue this loss rate is slow enough that we could replenish the atmosphere with ongoing effort. Others suggest we must find a way to recreate a protective magnetic field, or Mars will never hold on to the atmospheric gift we might give it. As we contemplate the transformation of Mars, we must begin with this stark reality. Mars is not a dead world awaiting resurrection. It is a world that has been fundamentally changed by planetary forces beyond our current ability to reverse. To terraform Mars is not to restore what was lost, but to create something entirely new, something that has never existed in the 4 billion year history of this rust-colored planet. The question is not whether Mars was once habitable, but whether humanity possesses the knowledge, resources, and generational patience to make it so again. Here, at our starting point, Mars remains as it has been for eons, cold, thin-aired, radiation-soaked, and waiting. Before we can measure the time required to terraform Mars, we must first understand what we truly mean by the word itself: terraforming. It sounds simple, transforming another world to be like Earth. But the reality is far more nuanced, layered with possibilities that range from modest shelters to a complete planetary metamorphosis. The term itself does not describe a single destination, but rather a spectrum of transformations, each with its own requirements, challenges, and timelines that stretch across centuries or even millennia. To terraform is not merely to create livable space. It is to fundamentally alter the physics, chemistry, and perhaps even the biology of an entire world. Yet within that grand ambition lie multiple thresholds, each representing a different level of achievement. Some scientists speak of paraterraforming, the construction of enclosed habitats where controlled environments allow life to flourish without changing the planet itself. Others envision ecopoiesis, the introduction of primitive life forms that slowly, generation by generation, begin to transform the atmosphere. And then there is full terraforming, the reshaping of Mars into a world where a human could stand on the surface, breathe deeply, and feel the warmth of a thickened atmosphere without any protective gear at all. The question becomes, which version of Mars are we creating? The answer determines everything that follows. At the most fundamental level, human survival without a pressure suit requires 3 critical conditions. First, atmospheric pressure must reach at least 6.3 kilopascals, roughly 6% of Earth's sea level pressure. This is known as the Armstrong limit, the threshold below which water boils at human body temperature. Below this pressure, exposed fluids in the body, saliva, tears, the moisture in lungs, begin to vaporize. Space itself becomes lethal, not because of cold or radiation alone, but because the human body cannot maintain its liquid equilibrium. Cross this threshold, and suddenly a pressure suit becomes optional, replaced perhaps by nothing more than an oxygen mask and warm clothing. But pressure alone is not enough. Temperature must also shift dramatically. Mars today averages -80 degrees Fahrenheit, cold enough to freeze carbon dioxide into dry ice. For liquid water to exist on the surface, even briefly, temperatures must rise above 32 degrees Fahrenheit, at least during the warmest seasons. For ecosystems to develop, for agriculture to become possible, Mars needs a climate where temperatures regularly hover between 40 and 70 degrees, a range where microorganisms can thrive, where ice melts into streams, where the soil becomes something more than frozen dust. The third requirement is breathable air, or at least survivable air. Mars's current atmosphere is 95% carbon dioxide, utterly hostile to human lungs. To terraform Mars completely would mean transforming that atmosphere into something resembling Earth's composition, roughly 78% nitrogen and 21% oxygen. But here we encounter a profound distinction. A habitable Mars is not necessarily an Earth-like Mars. Humans could potentially survive in an atmosphere with far less oxygen, perhaps 15%, supplemented by pressurized habitats or personal respirators. The planet could remain perpetually cold, its poles still locked in ice, its equator barely warm enough for liquid water, and yet humans could walk its surface, build cities, and call it home. This distinction between habitable and Earth-like shapes every discussion of timelines. Creating a minimally habitable Mars, one where humans need only light protective gear, could potentially be achieved in centuries. Creating a fully Earth-like Mars, one where forests grow naturally, where rain falls from clouds, where birds might one day fly. This could take tens of thousands of years, if it is even possible at all. Some researchers propose intermediate stages, milestones along the journey. Perhaps the first goal is simply warming the planet enough to unlock subsurface ice, allowing liquid water to flow seasonally in equatorial regions. This alone would be revolutionary, transforming Mars from a frozen desert into a world with lakes, rivers, and perhaps even shallow seas. The next milestone might be thickening the atmosphere to survivable pressure, even if the air remains unbreathable. Humans would still need oxygen supplies, but the threat of explosive decompression would vanish. Buildings could have windows. Airlocks could be simplified. The psychological burden of living on an alien world would lighten, if only slightly. Beyond these technical thresholds lies something more profound, the creation of a self-sustaining biosphere. A truly terraformed Mars would not depend on constant human intervention. It would breathe on its own. Photosynthetic organisms would regulate atmospheric composition. Water cycles would distribute moisture across the planet. Soil, enriched by organic matter, would support complex plant life. At this stage, Mars would no longer be a project requiring maintenance. It would be a living world, capable of supporting itself, evolving independently, perhaps even surprising us with ecosystems we never intended to create. Yet even this vision has variations. Some imagine a Mars covered entirely in vegetation, its rust-colored surface transformed into green plains and blue oceans. Others envision a more modest transformation. Isolated pockets of habitability scattered across a planet that remains largely unchanged. Oases in a desert that stretches horizon to horizon. The choice between these visions is not just scientific, it is philosophical, reflecting how we define success and what we value in a world remade by human hands. For the purposes of our timeline analysis, we must set a clear goal. We will focus on creating a minimally habitable Mars, a world where atmospheric pressure reaches the Armstrong limit, where surface temperatures allow liquid water to exist seasonally, and where the atmosphere, while not breathable, is thick enough to shield against radiation and provide meaningful weather patterns. This is an ambitious target, but not an impossible one. It represents a Mars where humanity could truly expand, where cities could grow beyond domes, where the next generation might look up at a sky that, while still alien, feels just a little more like home. The journey to this threshold is not a single grand gesture, but a series of deliberate, interconnected transformations, each building upon the last, each requiring technologies and timescales that test the very limits of human patience and ingenuity. We begin with the most elegant proposal, one that mirrors Earth's own atmospheric evolution. To warm Mars, we must first understand how planets hold heat in the silence of space. The greenhouse gas approach is perhaps the most intuitively appealing method for terraforming Mars. It asks us to consider, what if we could give Mars what Earth already has? An atmospheric blanket thick enough to trap the sun's warmth, transforming a frozen desert into a world where liquid water flows once more. This vision was championed most notably by aerospace engineer Robert Zubrin in the 1990s, whose writings painted Mars not as an impossible challenge, but as a world waiting for the right chemical key to unlock its potential. The concept is deceptively simple. Mars is cold, averaging negative 60 degrees Celsius, not primarily because it is farther from the sun, but because its thin atmosphere cannot retain heat. At just 0.6% the density of Earth's atmosphere, whatever warmth Mars receives during the day radiates back into space almost immediately. The planet cannot hold its breath. But if we could thicken that atmosphere with the right gases that trap infrared radiation the way a greenhouse traps sunlight, Mars might begin to warm itself. Zubrin proposed using super greenhouse gases, particularly perfluorocarbons or PFCs. These molecular structures are extraordinarily effective at trapping heat. Pound for pound, they are thousands of times more potent than carbon dioxide. On Earth, these gases are considered dangerous pollutants, contributing to climate change. On Mars, they could be salvation. A relatively small amount released continuously into the Martian atmosphere could, in theory, initiate a warming cycle that might become self-sustaining. The process would unfold like a cosmic awakening. As temperatures rise even slightly, the frozen carbon dioxide locked in Mars's polar ice caps, those brilliant white expanses that have remained unchanged for millennia, would begin to sublimate. This CO2 released into the atmosphere would itself act as a greenhouse gas, trapping more heat, which would release more CO2, which would trap more heat. A feedback loop, the same mechanism that drives climate change on Earth, but here deliberately engineered to resurrect a frozen world. Manufacturing these perfluorocarbons would require facilities on Mars itself. We would need to construct chemical plants capable of producing these gases from Martian resources, fluorine extracted from minerals in the soil, carbon from the atmosphere, and tremendous amounts of energy to power the synthesis. Some estimates suggest we would need to produce and release approximately 1,000 tons of PFCS per hour, sustained over decades, to initiate meaningful warming. The numbers are staggering, yet not impossible. They represent an industrial capacity comparable to a large Earth-based chemical manufacturing facility. The challenge is not whether we could build such a facility, but whether we could build it on Mars, maintain it remotely, or with minimal human supervision, and power it with the limited solar energy available at Mars's distance from the Sun. Nuclear reactors would almost certainly be necessary, perhaps dozens of them, their heat and electricity driving the continuous production of gases designed to warm an entire planet. Timeline estimates from various studies in the 1990s and early 2000s suggested that initial warming could occur within 100 to 300 years. This is not terraforming complete, not a breathable atmosphere or flourishing ecosystems, but the beginning of transformation. Within this time frame, surface temperatures might rise enough for liquid water to exist temporarily during summer days at the equator. The polar ice caps would begin their slow retreat, releasing not just carbon dioxide, but potentially water vapor, another greenhouse gas that would further accelerate warming. These were optimistic visions built on assumptions about Mars's carbon inventory. The calculations presumed that Mars's polar caps and regolith contained enough accessible CO2 to create a meaningful greenhouse effect once released. For years, this seemed plausible. Mars clearly had a thicker atmosphere in its ancient past. Perhaps that carbon was merely sleeping, waiting to be awakened. Then came the sobering analysis of 2018. A comprehensive study led by Bruce Jakosky examined all available data about carbon deposits on Mars, including measurements from orbital instruments and surface rovers. The conclusion was stark. There simply isn't enough easily accessible CO2 on Mars to create a substantial greenhouse effect through sublimation alone. Most of Mars's ancient carbon has been lost to space or locked deep within carbonate rocks, minerals that would require temperatures of 300 degrees Celsius or more to release their carbon, a requirement that creates a paradox. We need the carbon to warm the planet, but we need the planet to be warm to release the carbon. This finding does not eliminate the greenhouse gas approach. It refines it, adding layers of complexity to an already monumental challenge. If Mars's own carbon stores are insufficient, we must look elsewhere. We could manufacture greenhouse gases entirely from imported materials, perhaps mining asteroids for carbon and transporting it to Mars. We could target different gases entirely, focusing not on releasing what Mars has, but on creating what Mars needs from whatever elements are available. Some researchers have proposed using ammonia, which could potentially be harvested from asteroids in the outer solar system and crash deliberately into Mars. Ammonia is both a greenhouse gas and a source of nitrogen, which would be essential for building a breathable atmosphere eventually. Others suggest sulfur hexafluoride, another super greenhouse gas that could be manufactured from Martian sulfur deposits. Each alternative brings its own timeline, its own industrial requirements, its own cascading series of engineering problems. The greenhouse gas approach, once seen as the most straightforward path to warming Mars, now appears as one option among many, each requiring infrastructure we have not yet built, technologies we have not yet perfected, and resources we have not yet learned to extract from alien soil. Yet the fundamental principle remains sound. Mars can be warmed. The laws of thermodynamics do not forbid it. Greenhouse gases work the same way on Mars as they do on Earth. The question is not whether this approach could succeed, but how long it would take, and what it would truly cost to build the factories, deploy the reactors, and sustain the continuous industrial output needed to alter an entire planetary climate. As we consider these timelines, 100 years, 300 years, perhaps longer, we are forced to confront what it means to undertake a project that will not be completed in our lifetimes, nor in our children's lifetimes. The greenhouse gas approach asks us to think in terms of civilizations, not careers. It is engineering on a timescale that challenges our sense of urgency and our capacity for delayed gratification. But perhaps that is precisely the point. To terraform Mars is to commit to something larger than ourselves, to begin a process knowing that others, generations hence, will see its completion. The greenhouse gas approach is not just a method for warming a planet, it is a declaration that some dreams are worth beginning even when we cannot see their end. Above the rust-coloured surface of Mars, imagine a new dawn. Not the pale distant light that currently whispers across the frozen plains, but a focused beam of brilliance, concentrated and deliberate, warming the ice caps that have slept for billions of years. This is the vision of orbital mirrors and solar concentrators, structures so vast they would dwarf any construction humanity has ever attempted, yet elegant in their simplicity. Giant reflective surfaces positioned in space, angled precisely to redirect sunlight toward the Martian poles, melting frozen carbon dioxide and water ice, releasing greenhouse gases into the thin atmosphere below. It is not science fiction. It is engineering pushed to the edge of possibility. The concept is both ancient and futuristic. Humans have understood since the time of Archimedes that mirrors can concentrate light, focusing the sun's energy into a single powerful point. Now, we extend that principle across planetary scales. An orbital mirror would need to be enormous, potentially spanning hundreds of miles in diameter, yet remarkably thin, perhaps no thicker than a sheet of aluminum foil. Its purpose would be singular: to capture the distant sunlight at Mars's orbit, only 43% as intense as Earth receives, and redirect it where Mars needs it most. The polar regions, locked in perpetual cold, hold vast reservoirs of carbon dioxide, ice, and water. If warmed sufficiently, these reserves could sublime and evaporate, thickening the atmosphere naturally, accelerating the greenhouse effect without requiring endless bombardment of manufactured gases. From the surface of Mars, such a mirror would appear as a brilliant second sun, smaller perhaps, but intense, tracing a deliberate path across the sky. It would not illuminate the entire planet, but rather focus its energy like a magnifying glass held over kindling. Concentrated beams could raise temperatures in targeted regions by tens of degrees, perhaps more. The ice would begin to crack and hiss as it transformed directly from solid to gas. Carbon dioxide, released into the air, would trap more heat. Water vapor would follow, creating clouds, weather patterns, the first signs of an active climate. This is not instantaneous transformation. It is the patient work of decades, guided by machines that orbit in silent precision. Yet the engineering challenges are staggering. Building a structure hundreds of miles across in the weightlessness of space requires materials, manufacturing capabilities, and coordination beyond anything humanity has achieved. One possibility is to construct the mirrors in orbit around Mars itself, using resources mined from Phobos or Deimos, the planet's two small moons. These moons are composed largely of carbonaceous material and water ice, potential sources for the raw materials needed. Robotic factories could extract, refine, and assemble ultra-thin reflective films, unfurling them slowly like metallic petals opening in the void. Another approach suggests manufacturing components on Mars's surface and launching them into orbit. though this introduces the immense difficulty of escaping Martian gravity, even if it is only 38% of Earth's. The mirrors themselves would not be rigid structures. They would be flexible, gossamer-thin membranes held taut by centrifugal force as they rotate, or by tension wires stretching across lightweight frames. Some designs propose thousands of smaller mirrors working in concert, each independently controlled, adjusting their angles moment by moment to maintain focus as Mars rotates beneath them. Others envision a single colossal structure, a planetary parasol reversed, concentrating rather than blocking light. Either way, the precision required is extraordinary. A slight miscalculation in angle could scatter the beam uselessly across space, or worse, focus it too intensely, scorching rather than warming the surface below. The timeline for deploying such technology stretches across generations. Optimistic estimates suggest that with sufficient investment and technological advancement, the first experimental mirrors could be operational within 50 to 100 years. This assumes that we have already established significant infrastructure on Mars: mining operations, manufacturing facilities, orbital construction platforms, and the logistical networks to coordinate them all. It assumes mastery of autonomous robotics, capable of working for years without direct human supervision, assembling structures in the harsh radiation environment of space, repairing themselves when damaged by micrometeorites or solar storms. It assumes a level of international cooperation and resource commitment that has never been sustained for a single project in human history. But perhaps most importantly, orbital mirrors do not work in isolation. They are not a singular solution, but one element of a comprehensive approach. Used in combination with greenhouse gas manufacturing, mirrors could dramatically accelerate the warming process. While factories on the surface produce fluorinated gases that trap heat, mirrors would add direct thermal energy, creating a feedback loop. As temperatures rise, more ice melts, releasing more carbon dioxide and water vapor naturally, which traps even more heat, which allows the mirrors to work more efficiently on the remaining ice. The synergy between methods becomes greater than the sum of their parts. Some scientists propose even more ambitious variations. Solar concentrators could be positioned not just to warm the poles, but to power massive industrial complexes on Mars's surface, beaming concentrated solar energy to receiving stations that convert it to electricity. This energy could drive the chemical processes needed to manufacture building materials, fuel, oxygen, and synthetic greenhouse gases. In this vision, the mirrors serve dual purposes: planetary engineers by day, power plants by night, shifting their focus as Mars rotates, always working, always contributing to the transformation. The cost is difficult to comprehend. Estimates range wildly, from hundreds of billions to trillions of dollars, depending on the scale and sophistication of the designs. Yet cost must be measured not just in currency, but in time, expertise, and the opportunity cost of resources that could be used elsewhere. For the price of a single orbital mirror system, humanity could potentially build dozens of enclosed habitats, or fund centuries of scientific research. The question becomes not just, can we do this, but should we do this first? There is something poetic about using light itself as a tool of transformation. Sunlight, which has travelled 140 million miles through the void to reach Mars, would be carefully gathered, redirected, and used to awaken a frozen world. The mirrors would be silent sculptors, painting warmth onto ice, guiding Mars slowly toward a new state of being. They would hang in the Martian sky for centuries, perhaps millennia, quiet monuments to human ambition and patience. As we contemplate these orbiting giants, we must remember they represent more than engineering. They represent a choice about what kind of future we wish to build and how much we are willing to reshape the cosmos to achieve it. Long before the first human sets foot on Mars, a different kind of footprint is imagined in its skies. Not the soft imprint of a boot in red dust, but brief artificial suns blossoming high above the poles. For some, this is the most shocking proposal in all of planetary engineering. For others, it is simply an honest extension of what we already are, a civilization that has learned to harness the atom, now wondering if that power could reshape an entire world. When Elon Musk casually suggested we should nuke Mars, it sounded less like a science plan and more like a punchline. Yet hidden inside that phrase is a real, serious scientific question. Could controlled nuclear explosions be used to warm Mars quickly enough to jumpstart terraforming? To understand the idea, we first have to leave behind the image of warheads slamming into the surface. The more realistic concept places thermonuclear devices high in the Martian sky, above the polar regions, detonating in the thin upper atmosphere. Each burst would create a brief, intense flash of light and heat, a miniature star that shines for only seconds. That burst would vaporize carbon dioxide and water ice in the polar caps and in the upper soil, releasing greenhouse gases into the atmosphere. Imagine it as a violent substitute for sunrise. Instead of waiting for centuries of gentle sunlight to slowly warm the ice, you compress that energy into moments. A chain of detonations, carefully timed, would create a repeating pulse of artificial summers over the poles, each blast adding a little more gas to the air, a little more heat to the planet. On paper, the physics is straightforward. Nuclear weapons release enormous amounts of energy. Mars has large polar caps made of water ice and frozen carbon dioxide. Heat the caps, they sublimate. Greenhouse gases thicken the air. The planet warms. The logic is direct, almost seductively simple. But nature rarely rewards simplicity. When planetary scientists ran the numbers, how much CO2 is actually available, how much energy is needed, how much could realistically be delivered by bombs, the picture dimmed. The polar caps alone do not hold enough CO2 to build a thick, Earth-like atmosphere. Even if you liberated nearly all of it, Mars would likely still be cold and thin-aired, just a slightly less hostile version of itself. And then there is the fallout. Even detonated high in the atmosphere, nuclear devices would inject radioactive materials into Mars's environment. Mars has no thick protective air, no strong magnetic shield. Radiation would linger, dust would carry contaminants across the planet. For a world we someday hope to walk freely, grow food on, and perhaps call home, deliberately bathing it in fallout feels like drawing graffiti on a blank canvas before the painting has even begun. The science community's verdict, for now, is cautious. As a primary terraforming tool, nuclear bombing seems both inefficient and messy. Enormous political, ethical, and engineering challenges for only a partial climatic gain. The idea is not laughed away, but it is set gently on a high shelf labelled extreme, unlikely, not impossible. Yet this is where the story turns, because the phrase nuclear solutions does not end with bombs. In fact, its most promising chapter may be far quieter, not flashes in the sky, but steady heat humming in the Martian night. If nuclear detonations are like matches struck in a storm, nuclear reactors are like campfires built carefully from stone and steel. Instead of one colossal burst of energy, reactors provide a continuous, controllable source of heat and electricity, exactly what a slow, patient terraforming effort needs. Picture compact nuclear reactors buried just below the surface near Mars' polar regions. Not weapons, but power plants. Their heat seeps into the surrounding ice, slowly carving out subsurface lakes and melt channels. Over years and decades, these reactors could turn buried reservoirs of frozen water into accessible liquid, feeding sealed habitats, greenhouses, and industrial processes that release and recycle gases. Closer to the equator, reactors could power vast arrays of machines, compressors turning thin Martian air into stored oxygen, factories producing greenhouse gases tailored to be efficient and long-lived, even massive heaters warming dark, dusty plains that never see enough sunlight to melt on their own. Nuclear energy here is not a single grand gesture, but an infrastructure, an invisible backbone supporting everything from early exploration to large-scale climate engineering. The radiation from these reactors is not sprayed across the planet, but contained, shielded, and managed. We already operate nuclear submarines in the depths of Earth's oceans for decades at a time. On Mars, that same technology becomes a lifeline. In a world where solar power falters during prolonged dust storms and nights last as long as a Martian day, a stable nuclear core offers something priceless: continuity. How effective would this be? Not overnight, not in a human generation, perhaps not even in 3. Nuclear reactors can melt ice, power factories, and help drive localized warming and atmospheric processing. But turning that into global change, raising average temperatures, thickening the air, reshaping the climate, moves us into a timeline described not in years, but in centuries. Decades to establish an initial nuclear grid, more decades to expand it, to scale up production of greenhouse gases, to continuously tap subsurface ice. A few centuries before the cumulative effects might be obvious from orbit. More clouds, more haze, perhaps darkened polar regions where ice has retreated. Nuclear power does not give us a shortcut around planetary time. It simply lets us participate in it more meaningfully. And yet, this long view is precisely why the nuclear path is not as outlandish as it first appears. When people hear nuclear terraforming, many imagine reckless blasts and scorched landscapes. But the deeper conversation is about energy density. To change a planet's climate, you must move unimaginable amounts of heat, gas, and ice. The sun does this slowly for free. If we want to speed it up, we must bring an energy source capable of competing, even slightly, with that daily diffuse solar input. Chemical fuels are too weak, solar panels too intermittent at Mars's distance. Fusion is still a dream. Fission, old, imperfect, controversial, stands today as the only mature technology that can deliver sustained, high-power output on another world from relatively small, transportable masses. Used as bombs, it is a sledgehammer. Used as reactors, it is a scalpel. In any realistic vision of faster terraforming, nuclear power is not alone. It works alongside the mirrors that brighten the poles, the greenhouse gases manufactured in buried factories, the imported comets and asteroids that deliver fresh water and carbon. Bombs, if they are ever used, would likely be a short, early, tightly regulated phase, if at all. Reactors, by contrast, would be the quiet workhorses, powering the entire enterprise over lifetimes. Perhaps in some distant century, standing on a softened Martian plain under a thicker, hazier sky, someone will look up at a faint glimmer of aurora and know, this air was not always here. It came from ice and rock, from light and time, and from small suns we built and confined inside steel. Nuclear fire, once feared only as an ending, repurposed as the slow, persistent beginning of a new kind of world. Far above the thin skies of Mars, beyond the reach of any dust devil or polar frost, lies a different kind of solution, not in the rusted rocks or buried ice of the planet itself, but in the silent traffic of the solar system. Asteroids, comets, frozen remnants of worlds that never were. If warming Mars is like trying to heat a vast abandoned house, then these bodies are the forgotten fuel tanks stored in the attic of the solar system. They carry the ingredients Mars is missing: water to thicken its rivers and seas, nitrogen to pad its fragile air, and powerful greenhouse molecules that could turn a dim, distant sunlight into something life can actually use. To terraform a planet, we may have to move mountains. In this case, mountains made of ice and rock falling from the sky. We start by looking outward, scanning the darkness for blue-white glints of ice. Some asteroids, especially those in the outer belt and beyond, are rich in water locked inside minerals or frozen in their cores. Comets, drifting in long, elegant orbits from the Kuiper belt or Oort cloud, are even richer, icy relics, half water, half dust, laced with carbon compounds and frozen gases. To Mars, these are not just celestial curiosities. They are cargo. Imagine a future observatory hovering near Mars, lenses and radar sweeping across millions of miles. Its task is patient, almost meditative. Find the right targets. Bodies just large enough to be worth moving, just icy enough to matter, just aligned enough with Mars' path that, given time and precision, they can be nudged onto a collision course or into a gentle capture. This is not a plan measured in years or even in decades. It is measured in orbits. To change the trajectory of an asteroid or comet, we do not grab it and yank. We whisper to it again and again across many passes around the sun. Robotic tugs could dock on its surface, firing small thrusters at carefully chosen angles. Solar sails could be attached, letting the pressure of sunlight slowly bend its path. In more speculative visions, concentrated beams of light or even focused plasma engines nudge its orbit, one fraction of a mile per hour at a time. Over years, tiny changes grow into massive shifts. Over centuries, a once harmless stone drifting far from Mars can be transformed into a targeted delivery of water and gas. Some of these bodies do more than just bring ice. Certain asteroids and distant icy moons are rich in ammonia, NH3, a compound of nitrogen and hydrogen. On Mars, ammonia is a prize twice over. Break it apart, and the nitrogen can help build a thicker, more Earth-like atmosphere. Leave some of it to linger, and ammonia itself becomes a powerful greenhouse gas, trapping heat far more efficiently than carbon dioxide ever could. In some scenarios, entire ammonia-rich chunks, perhaps fragments of Kuiper belt objects or repurposed icy moons, are redirected toward Mars. As they plunge into the atmosphere, friction and shock tear their molecules apart. Ammonia breaks into nitrogen and hydrogen. The hydrogen flees to space, light and restless. The nitrogen stays, joining the thin Martian air, molecule by molecule, impact by impact. If Mars is a stage awaiting air and water, then these imported bodies are the deliveries arriving at the back door, each one unpacked by gravity and fire. But the elegance of the idea hides a brutality. Dropping even a modest comet onto Mars is not a gentle rain. It is a planetary event. A single 10-kilometer object, traveling at tens of thousands of miles per hour, releases energy measured in millions of megatons of TNT. Local crust melts. Shock waves circle the globe. Dust, vapor, and steam erupt into the sky, darkening the sun for months or years. For a world we hope to make habitable, each impact is both a gift and a wound. How many such blows would be needed? The numbers are sobering. To give Mars an atmosphere with pressure, even a fraction of Earth's, we are talking about importing billions of tons of material. One large comet might deliver enough water to fill a modest terrestrial sea, yet Mars would need many such gifts to carve out oceans, lakes, and deep aquifers. To build up nitrogen to Earth-like levels, engineers estimate we might need hundreds, perhaps thousands, of impacts by ammonia-rich bodies over centuries. From a cosmic perspective, this is entirely possible. The solar system is not short on ice and rock. But from a human perspective, it is an engineering project stretched across the lifetimes of civilizations. And then there is the question of control. Redirecting a comet is not like steering a plane. It is like setting a boulder rolling down a mountain and trusting your calculations to predict exactly where it will stop. Slight errors early in the process can become catastrophic deviations decades later. If we aim too shallow, the comet might skip off Mars's thin atmosphere and continue into deep space, lost after a century of planning. Too steep, and the impact could sterilize a hemisphere we intended to protect. A tiny miscalculation could send our carefully guided missile not to Mars, but somewhere else entirely, perhaps even back toward the inner solar system, where Earth and its fragile biosphere reside. With timelines stretched over centuries, safety becomes more than a technical question. It becomes a cultural one. Can multiple generations maintain the vigilance, funding, and global cooperation needed to keep watch over objects we have set into motion long before they arrive? Can one civilization commit another to sky-shaping decisions made hundreds of years earlier? Uncertainty seeps in here, not as a flaw, but as an honest boundary. We can simulate trajectories, model impacts, estimate how much water and nitrogen we might unlock. But how human societies will choose to wield that power, cautiously, boldly, or not at all, remains beyond any calculation. There is another subtle challenge. Mars is not empty. By the time we are ready to throw comets at it, we may already have research stations, mining outposts, perhaps even early habitats dotting its surface and orbit. Each impact must be planned with those fragile footholds in mind, scheduled and aimed so that new craters and atmospheric pulses do not erase a century of progress in an afternoon. Some proposals imagine a gentler approach. Instead of direct impacts, icy bodies could be parked in orbit around Mars, slowly mined and vaporized. Giant mirrors or focused microwaves could turn them into artificial comets whose tails are carefully bled into the atmosphere over decades, not seconds. It would be slower, but more controlled, terraforming by steady infusion rather than explosive delivery. Between these extremes, violent bombardment and patient sublimation, lies a wide landscape of ideas. The truth is, we do not yet know which path, if any, future engineers will choose. And in that uncertainty is a quiet freedom, the recognition that our descendants may invent entirely new ways to move worlds that we have not yet imagined. What we can say is this: importing volatiles from asteroids and comets is not a quick fix. It is not the work of a single mission or a single generation. Identifying the right objects could take decades, redirecting them another century or two. Allowing Mars to respond, its atmosphere to thicken, its climate to stabilize, would require yet more time, stretching the effort across 3, 4, or even 500 years. To terraform Mars with falling moons and engineered comets is to think not in election cycles, but in epochs. Yet there is something profoundly human about the idea. For as long as we have existed, we have watched comets blaze across the sky as omens, as messengers, as harbingers of change. In a future where we try to reshape an entire planet, those same messengers become collaborators, not symbols of fate, but instruments of intention. In the end, importing volatiles is less about throwing rocks at Mars and more about learning to choreograph with gravity, to take the debris of planetary formation and repurpose it, turning leftover fragments into the seeds of seas and skies. If we ever reach that point, redirecting worlds to nourish another world, we will have crossed an invisible threshold. Terraforming will no longer be a thought experiment, but a lived practice of celestial engineering, written not in blueprints, but in orbits and impacts and the slow, patient accumulation of air. As we imagine Mars slowly turning blue and white beneath a thicker sky, another, quieter question begins to surface. Not about how to build an atmosphere, but how to keep it. For Mars, this is not a hypothetical concern. It is a memory. Once, billions of years ago, Mars may have worn a sky not so different from a young Earth. Rivers carved valleys. Ancient shorelines still trace the edges of long-vanished seas. Minerals whisper of liquid water that stayed, not for days, but for ages. For all of this to exist, Mars must once have had a thicker atmosphere, warm enough and dense enough to let water flow freely. Today, that world is gone. What happened in between is the story we have to understand before we can dare to rewrite it. On Earth, we live inside a protective cocoon, a magnetic field generated by a churning metallic core. This field stretches far into space, a vast invisible bubble called the Magnetosphere. When the solar wind, a constant stream of charged particles from the sun, slams into this bubble, it is deflected, guided around us like water around a rock in a river. Our atmosphere is not merely held by gravity, it is shielded by magnetism. Mars, long ago, may have had something similar. Crustal rocks on its surface are magnetized in patterns that suggest an ancient global magnetic field, one that switched on and off like Earth's does over geologic time. But somewhere between 4.2 and 3.8 billion years ago, that field faded. The Martian core cooled. Its internal dynamo, whatever once stirred it into motion, slowed and then fell silent. The planet's magnetic shield collapsed. Without that shield, Mars was left exposed. The solar wind did not simply brush past anymore, it bit. High-energy particles slammed directly into the upper atmosphere, knocking atoms and molecules away from the planet's grip, especially the lighter ones like hydrogen. Over millions of years, the slow, invisible sandblasting of space thinned the Martian sky. Water molecules broken apart by radiation lost their hydrogen to space. CO2 was stripped from the fringes of the atmosphere. What remained grew colder, thinner, more fragile. This was not a sudden cataclysm. It was erosion written in centuries and eons instead of waves and rain. NASA's MAVEN mission, orbiting Mars today, is essentially watching this process in real time. It measures how much atmosphere is being removed right now by the solar wind. The answer is humbling and somewhat reassuring at the same time. Mars is still losing air, but very slowly, not in months or years, or even human lifetimes. On average, MAVEN suggests Mars is losing the equivalent of a small fraction of its total atmosphere every million years. That timescale matters for our dream of terraforming. Once we imagine that we have thickened Mars's atmosphere, warming the planet, darkening the polar caps, maybe filling low basins with new seas, the solar wind once again becomes a problem. But it is not a thief in the night. It is a slow accountant, shaving tiny amounts off a very large balance. If we somehow gave Mars a dense, Earth-like atmosphere tomorrow, how long would it take for the solar wind to strip it away again? With current data, the answer appears to be Not in 1,000 years, not in 10,000. More like tens to hundreds of millions of years. The exact number depends on many things: how thick the atmosphere is, its composition, how active the sun is over time. But the core idea remains: atmospheric loss by solar wind is real, but it is slow on human timescales. This leads us to a delicate, almost philosophical question in planetary engineering. Do we need to solve the magnetosphere problem first, or can we build the sky and worry about the shield later? Some scientists argue that a full magnetic solution can wait. If atmospheric loss takes millions of years, then for the first few centuries, or even millennia, humanity could simply maintain the new Martian atmosphere artificially. We could continue producing greenhouse gases. We could replenish water lost to space with imported ice from comets and asteroids. Terraforming becomes not a one-time transformation, but an ongoing process of maintenance. Others see this as building a city on a slowly crumbling cliff. Yes, the erosion is glacially slow compared to our lives, but a truly stable, independent biosphere on Mars might require us to address the root problem: the lack of a global magnetic field. Not because Mars will lose its air in our lifetimes, but because civilization, if it endures, will eventually feel the cost. This is where an audacious idea from NASA researchers enters the story: an artificial magnetic shield. Instead of trying to restart Mars's core, a feat far beyond our current imagination, they propose placing a powerful magnetic field generator at a special point in space, the Mars-Sun L1 Lagrange point. This is a gravitational balance point about 1 million kilometers in front of Mars, directly between the planet and the Sun. From this vantage, a magnetic field could be inflated outward like a protective umbrella. When the solar wind rushes in, it would be deflected and guided around Mars, just as Earth's natural magnetosphere does. Mars itself would sit in the shadow of this artificial magnetic bubble, sheltered from the brunt of the solar wind. The concept is simple in description and staggering in implication. A machine floating in the void, generating a magnetic field strong enough and wide enough to wrap an entire planet in its protection. If such a shield were built and powered, the model suggests something remarkable. Mars's atmosphere would not just stop eroding so quickly. Over time, the reduced stripping combined with continued volcanic outgassing and ice sublimation could even allow the atmosphere to slowly thicken on its own. The planet, in a sense, could begin helping itself. The shield proposal resides somewhere between science fiction and early engineering study. The physics of creating such a field is understood. The technologies, superconducting loops, plasma fields, massive power sources, are extensions of what we already build in particle accelerators and fusion experiments. But scaling them up to planetary size is a challenge measured not in blueprints, but in generations. And yet, the timescale for deploying a first-generation shield is not as distant as it might seem. If humanity remains committed to Mars, the infrastructure we'd need, heavy lift rockets, large-scale in-space construction, nuclear or solar power stations in orbit, are technologies that many space agencies and companies are already contemplating for other purposes. As those mature, a magnetic shield at L1 shifts from fantasy to long-term project. Rough estimates suggest that once we are routinely operating in cislunar space and beyond, and once Mars has a permanent human presence, a serious attempt at an L1 magnetic shield could arise within 20 to 50 years of that era. That does not mean it would instantly be built or work perfectly. The first versions might be small, experimental, only partially effective. but they would mark the beginning of planetary-scale engineering not just on surfaces, but in the space around a world. This brings us back to our timeline question. Do we have to wait for a magnetic shield before we start thickening the Martian atmosphere? With what we know today, the answer appears to be no. Atmospheric loss is slow enough that for the first phase of terraforming, stretching across centuries, humanity could rely on active maintenance and replenishment. The magnetosphere problem is not an immediate barrier. It is more like a distant horizon we will eventually have to address if we want Mars to be truly, deeply stable. Terraforming, in this light, is not a single countdown to a finished world. It is a layered project. First, we warm. Then we thicken. Then we seed with life. And parallel to all of this, perhaps, we learn how to bend not just air and water, but magnetism itself to our needs. Somewhere in the space between Mars and the Sun, in the quiet equilibrium of the L1 point, we might one day see the glow of human engineering. A ring, a station, or a field generator humming in the dark, turning invisible lines of force into a planetary shield. If the first steps of terraforming are about giving Mars back its air, the magnetosphere problem asks a deeper question. How long do we want that gift to last? 1,000 years? 1,000,000? As we turn toward biological terraforming, the slow introduction of microbes, lichens, and eventually forests, this question will hover in the background. Because life does not think in decades, it thinks in eras, and Mars, once given a sky, may ask us to think that way too. Long before forests sway under a Martian sky, before rivers carve new valleys in rust-red rock, the first true Martian settlers will arrive silently, not in starships, but in cargo canisters no bigger than rooms. Their names are unfamiliar, their shapes microscopic. Extremophiles, cyanobacteria, lichens that cling to stone like slow, patient fire. If the earlier stages of terraforming are about physics and engineering, mirrors, reactors, magnetic shields, this stage is about something far stranger, asking life itself to rewrite a planet. Our journey into biological terraforming does not begin with trees or grass, but with organisms that, on Earth, seem almost like science fiction. Microbes that survive boiling acid, bacteria that shrug off radiation that would kill a human 1,000 times over, tiny cells that feast on rock and exhale gases, slowly, relentlessly changing the air around them. On Mars, these will be the first true pioneers. At first, the planet will still be harsh. Even after we thicken the atmosphere and warm the ground, temperatures will swing wildly. Dust storms will sweep across plains now dimly lit by a swollen, hazy sun. Yet in sheltered basins, inside craters warmed by orbital mirrors, along the shores of newly formed ephemeral lakes, the first experiments will begin. Tiny habitats, biodomes, rock-covered vaults, buried greenhouses, will serve as laboratories for planetary evolution. Here, extremophile microbes from Earth will be tested against Martian soil and water. Some will fail, many will die, but others will adapt, or be helped to adapt, by the careful hand of genetic engineering. On Earth, life has already proven it can endure conditions that resemble a young Mars. In Antarctica's dry valleys, microbial mats sleep in frozen ground for years, awakening only when trickles of meltwater pass by. In Chile's Atacama Desert, one of the driest places on the planet, certain bacteria and algae draw water directly from the thin morning air. In nuclear reactors, the bacterium Deinococcus radiodurans knits its shattered DNA back together after exposures that would turn human cells to dust. These are not exceptions. They are reminders of how resourceful life can be when given even the faintest foothold. The first generations of Martian microbes would likely be chosen not just for survival, but for purpose. Some would be chemolithotrophs, organisms that eat rock, extracting metals and nutrients, while subtly changing the chemistry of the soil. Others would fix nitrogen, if we have managed to deliver enough of it, turning an inert gas into a usable resource for future ecosystems. But one group, ancient and unassuming, will be central to the long arc of change: cyanobacteria. Billions of years ago on Earth, cyanobacteria transformed our own atmosphere. In shallow seas under a dimmer sun, they absorbed carbon dioxide, took in water, and used sunlight to split molecules apart. Their waste product was oxygen, at first a toxic, corrosive gas to most existing life. Slowly, over hundreds of millions of years, that waste reshaped the sky, turning a suffocating blanket of CO2 into the breathable air we know today. Martian cyanobacteria, if we choose to release them, would be asked to do something similar on a colder, thinner, harsher world. Imagine shallow, artificially warmed ponds scattered across the Martian surface, each a controlled experiment, lined with nutrients imported or mined. Within them, cyanobacteria bloom in long green strands, their colonies forming mats that undulate gently in the weak Martian breeze. Above them, the faint sun glints off a slowly condensing atmosphere, still too thin to breathe, but no longer entirely alien. The process of oxygenating Mars, however, will not be quick. Even in optimistic models, with abundant water, sunlight, and nutrients, turning Mars from red to blue-green is not a project measured in decades. It is measured in centuries, or more likely, millennia. For oxygen to build up in the atmosphere, not only must it be produced, it must also have nowhere left to go. On early Earth, oxygen first reacted with iron in the oceans and crust, rusting entire layers of rock. Only after these sinks were saturated did oxygen accumulate in the sky. Mars, with its iron-rich dust and chemically reactive surface, would present a similar obstacle. For hundreds of years, maybe thousands, most of the oxygen produced by cyanobacteria might vanish into the ground, binding with minerals, vanishing into stone. From our vantage point, living through perhaps 70 or 80 of those years, it would be easy to call this failure. But on planetary timescales, this is preparation, a slow, invisible priming of the crust, setting the stage for a later atmospheric bloom. Genetic engineering could bend this process, but not completely escape it. We might design microbes with thicker protective shells to resist radiation, or metabolic pathways tuned to the chemistry of Martian regolith. We could create cyanobacteria that are more efficient at photosynthesis, or that secrete protective films to trap moisture and create microhabitats for other species. We may even engineer entirely new forms of lichen, hybrids of fungi and algae, or fungi and modified cyanobacteria, designed specifically for Mars. These organisms on Earth already perform a quiet miracle. They colonize bare rock, etching their way into it with acids, trapping dust, collecting water from air so thin it barely seems to exist. Over decades, then centuries, their bodies build the first fragile soils in places once thought sterile. On Mars, we would ask lichens to do the same thing, but on a scale that stretches across continents. The idea is not to seed forests overnight, but to follow a principle ecologists call succession. Life rarely appears fully formed in a mature ecosystem. Instead, it comes in waves. First, the pioneers, hardy microbes, lichens, algae, moss-like analogues. They do not require rich soil, They create it. Their bodies, when they die, become the first organic matter mixed into the dust. Their chemical activity releases trapped nutrients from rock. Over centuries, the ground gradually changes from sterile regolith into something that begins to resemble soil. Next come slightly more complex plants, engineered grasses, small shrubs, tough ground cover. These would likely not be Earth species copied exactly, but tailored descendants designed to tolerate low pressures, high UV light, and wide temperature swings. Their roots would stabilize dunes. Their leaves, scattered across millions of square kilometers, would increase atmospheric oxygen production and water vapor cycling. Only after many such waves, and after a long, delicate balancing act between atmospheric engineering, radiation protection, and biological resilience, would we finally contemplate trees. Imagine walking along the edge of a shallow Martian valley 1,000 years from now. Above you, small stunted trees cling to the slope, their roots gripping soil that was once just iron oxide dust. Their leaves might be darker than Earth's, tuned to capture more of the weak sunlight. In the distance, a patch of lichen-covered rock glows faintly green under the cold morning sun, a reminder of the first settlers that began this transformation. Even then, even in this imagined future, the air might still not be fully breathable. A thick atmosphere is not automatically a safe one. Carbon dioxide levels would likely remain high for a long time. Oxygen might be present in significant quantities, but not yet at the 21% our bodies require without assistance. The question we often ask, when could humans walk on Mars without a suit and simply breathe, is not just about time, it is about thresholds. According to many estimates, raising Mars to that threshold purely through biology and imported volatiles could take thousands of years, perhaps 5,000, perhaps 50. Our uncertainty here is not just scientific, it is existential. We have never done this before. We have no other terraformed worlds to compare against. Some scenarios suggest an intermediate stage, an atmosphere thick and warm enough that we no longer need full pressure suits, only oxygen masks, a sky tinted faintly green and orange, with wisps of cloud catching the pale sunlight. Standing there, we might feel wind on our faces, hear it carrying dust across a landscape that now smells faintly of soil and distant, bitter plants. A partial victory, but a profound one. Genetic engineering might accelerate these stages, but each acceleration carries risk. Inviting life to cover a planet is not like painting a surface. It is like lighting a fuse. Once billions of organisms are reproducing, mutating, and adapting across an entire world, control becomes a matter of influence, not command. We might design Martian ecosystems carefully, choosing species combinations that support one another in fragile new food webs, microbes that feed on minerals, fungi that break down dead matter, plants that share nutrients through root networks. Over time, these webs would likely evolve beyond our initial intentions. Some view this as a danger, others as the necessary price of creating a truly living world. Somewhere along this arc of centuries and millennia, the story of Mars shifts. It stops being solely a human engineering project and becomes something more like a collaboration between physics and biology, between geology and genetics, between our plans and whatever emergent patterns life invents for itself. The day a human removes their helmet on Mars and breathes deeply, lungs filling with air that has never touched Earth, will not be the result of a single moment of brilliance. It will be the culmination of countless tiny, patient acts, microbes dividing in a dark, salty pool, lichens clinging to a wind-scoured rock, the first leaf unfurling under a weak, distant sun. In that breath will be the memory of billions of years of evolution on Earth, exported across space and invited to begin anew. And in that moment, we will realize that terraforming is not just about changing a planet. It is about asking life how far it is willing to go. We have imagined warming seas beneath a dusty sky, forests clinging to the slopes of ancient craters, rivers carving new stories into Martian rock. But beneath every vision lies a quiet, inescapable question. What would it actually cost to do this? Not in dollars alone, but in energy, in metal, in human lifetimes. On Earth, we measure power in gigawatts, the output of a large power plant or an entire nation's grid. Terraforming Mars pushes us into a different language. Here, the unit is the terawatt, 1 trillion watts, burning not for minutes or hours, but for centuries. To raise Mars by tens of degrees, to free carbon dioxide from polar caps and buried ice, to split water and build a breathable atmosphere, we would need to pour energy into the planet the way a star pours light into space. Some estimates suggest we might need sustained power levels of 10 to 100 terawatts over hundreds of years to significantly transform the climate. For comparison, all of human civilization today runs on roughly 18 terawatts. In other words, terraforming Mars is not just another project. It is the equivalent of dedicating a large fraction of an entire civilization's energy output to a single world, and maintaining that effort for longer than any nation, empire, or corporation has ever existed. How do you even begin to supply that? On Mars, energy is not something we import in tanker ships. It must rise directly from the planet and its surroundings. Vast solar farms shimmering on the dusty plains, nuclear reactors humming beneath regolith, perhaps one day fusion plants burning hydrogen from captured comets. In orbit, kilometer-scale solar power stations could beam energy down to the surface in tight, focused microwaves, turning Martian deserts into power fields. Each technology is a chapter in an industrial story, one that Mars would have to write for itself. To build an atmosphere, you need factories. To build factories, you need mines. To run mines, you need power. And to sustain power at planetary scales, you need an industrial capacity that makes anything on Earth today look like a prototype. Imagine entire regions of Mars given over to production, refineries, where imported asteroids are melted and separated into metals and volatiles, chemical plants that manufacture super greenhouse gases, molecule by molecule, and release them to the sky, foundries printing mirrors as large as cities, then launching them into orbit on electromagnetic rails stretched across the landscape. This is not one factory here, one research base there. This is a planetary supply chain. Iron and aluminum pulled from ancient lava plains, water mined from subsurface ice, carbon extracted from the air, then locked into plastics, composites, and fuels. Over time, Mars would begin to resemble a slowly awakening organism, with industrial organs distributed across its surface, each performing a specialized function: power, extraction, processing, launch, construction. But who runs all of this? Even with advanced robotics and AI, humans remain at the center, not as individual heroes, but as a civilization. Early on, Mars can be built and maintained by a few thousand people with heavy automation, much like an Antarctic research network, multiplied and stretched across a world. But terraforming is not an outpost project. It is generational. To operate planetary-scale infrastructure, maintain millions of machines, govern settlements, educate the next wave of engineers and scientists, and cultivate something resembling a culture rather than a camp, Mars would likely need a population in the millions, then tens of millions. Not all at once, and not all in one place, but spread across hubs, crater cities, underground valleys, orbital stations. Think of it this way. The Apollo program, a brief moment in our history, engaged hundreds of thousands of people on Earth to visit one small region of the Moon for a few days at a time. Terraforming Mars is a project that never turns off. It is more akin to operating the entire global shipping industry, all power grids, all steel production, and all air travel simultaneously, except on another planet. How much would that cost in money? Any exact figure becomes absurd the moment we say it. Trillions of dollars certainly, perhaps tens or hundreds of trillions, spread over centuries. For context, the largest mega projects in human history, the US interstate highway system, China's high-speed rail network, the International Space Station, each cost on the order of a few $100 billion up to $1 trillion in today's money. Terraforming Mars would be more like building thousands of ISS-sized projects, plus a global transportation network, plus a new industrial base, all under harsher conditions than Antarctica, all farther away than the Moon. And yet, we do have historical rhymes. The construction of the pyramids, cathedrals, and Great Wall systems represented multi-generational commitments of resources and labor, sustained by belief, politics, and identity. The space race compressed nearly unimaginable investment into a single decade, driven by rivalry and wonder. The digital revolution poured trillions into an invisible infrastructure of code and fiber optics that reshaped the human experience without ever being seen from orbit. Terraforming Mars would sit at the unnatural crossroads of all of these, a feat of engineering, a symbol of civilizational ambition, and a bet on a distant future that those who begin the work will never see completed. How could such a project be financed? Traditional models, single governments writing checks, single corporations funding ventures, begin to dissolve at these scales. Instead, we may be looking at layered economic systems, Martian industries exporting high-value products to Earth, data and intellectual property flowing back as revenue, tourism to the red world becoming not fantasy but luxury, and perhaps entirely new markets born in low-gravity manufacturing and asteroid resource extraction. In that sense, Mars must first learn to pay its own way. Before the planet can be terraformed, it must be economically alive. A self-sustaining, diversified economy on Mars would likely be a prerequisite, not a side effect. Only when Martian industries can build their own reactors, mine their own materials, grow their own food, and finance their own infrastructure, largely independent of Earth, does terraforming shift from dream to long project. Until then, early efforts may look more modest. Local climate control around cities, domes and paraterraformed valleys, experimental atmospheric processes that alter the sky just enough to teach us what comes next. There is another cost as well, one harder to count: attention. Terraforming Mars would demand a commitment across centuries of shifting politics, changing cultures, and evolving technologies. Empires will rise and fall, corporations will appear and vanish, yet the machines on Mars would need spare parts, the reactors would need fuel, the atmosphere would need monitoring. Can a civilization maintain focus on a single planetary goal for that long? That question may be as important as any equation about terawatts and tons of steel. Because in the end, the true price of terraforming Mars is not just the energy we generate, the mines we drill, or the money we spend. It is the decision to weave an entire world into our story. and to accept that the payoff lies not in quarterly reports or election cycles, but in the distant gaze of people not yet born, standing one day on Martian soil, breathing a sky their ancestors built. We leave the realm of single ideas and isolated technologies and step back far enough to see the whole arc of time. Terraforming Mars is not a mission. It is not a decade. It is not even a century. It is a sequence of eras, each one laying down a thin, fragile layer of possibility for the next. To understand how long it would really take, we have to stop thinking like engineers on a launch schedule and start thinking like geologists watching continents drift, or like biologists watching forests reclaim a barren landscape, inch by slow inch. Mars does not yield to blueprints. It responds only to time. Phase 1. Initial infrastructure and study, 2030s to 2060s. Our story begins soon, within the span of a human lifetime. In the 2030s and 2040s, the first long-term bases dig their foundations into Martian regolith. Habitat domes are inflated, buried, sealed. 3D printers hum in the thin air, turning local dust into bricks, beams and landing pads. This is not yet terraforming. It is learning how not to die. For decades, the focus is survival and measurement. Orbiters map the subsurface ice with radar so precise it can trace buried glaciers beneath ancient valleys. Ground stations track dust storms across entire seasons, building a weather record where none existed before. Robots drill into rock that has not seen sunlight for billions of years, searching for trapped water, salts, and perhaps fossil hints of microbes that once swam in vanished seas. Small experimental domes bloom like glass bubbles on the surface. Inside, closed ecological systems are tested. Algae ponds, soil bacteria, dwarf crops. Not to transform the planet, but to transform our understanding of what can live here and how. Even modest experiments, melting a few meters of permafrost, releasing a tiny plume of CO2 beneath an insulated cover, help answer the question, if we push Mars, how does it push back? By the 2050s and 2060s, orbiting power satellites, nuclear reactors, and large-scale mining operations may dot the Martian landscape. Fiber optic cables connect equatorial research stations to polar resource hubs. Mars becomes, for the first time, an interconnected world. Terraforming remains a whispered intention, not an official plan, but the pieces, the data, the tools, the energy are quietly assembling. Phase 2. Atmospheric warming begins, 2060 to 2200. At some point, a threshold of confidence is crossed. The models are good enough. The political will, or perhaps the economic incentive, turns. What was once pure speculation becomes a program. The second phase begins simply. We try to make Mars less cold. In the late 21st and early 22nd centuries, orbital mirrors the size of small cities unfurl above the poles, their ultra-thin films catching sunlight and reflecting it downward. On the ground, factories inhale carbon-rich rock and exhale greenhouse gases, CO2, perfluorocarbons, and other molecules engineered to trap heat with brutal efficiency. These factories may be entirely robotic, powered by nuclear reactors and fields of dust-resistant solar panels that track the waning sun. Year by year, degree by fragile degree, the average temperature inches upward, not enough to melt oceans, not yet, but enough to begin sublimating the vast frozen CO2 caps at the poles and in buried deposits. Every extra molecule of gas liberated into the sky adds a little more insulation, which melts a little more ice, which thickens the atmosphere further. If the loop is strong enough, it becomes a slow planetary scale feedback. From orbit, the change would be subtle, almost disappointing. Mars does not turn blue. It merely grows softer in outline, its polar caps shrinking slightly, its dust storms rising a bit higher, lingering a bit longer in a thicker air. On the surface, however, the difference is profound. A world that once plunged to temperatures where steel could crack now hosts regions that hover only just below freezing for parts of the year. This era lasts not decades, but centuries. From roughly the 20-teens through the 2020s, warming is an act of patience. Technologies improve. Early mirrors are replaced with lighter, more efficient designs. Greenhouse factories become more numerous, then partially self-replicating, crawling slowly across the plains like mechanical lichens, leaving altered atmosphere in their wake. And always, scientists watch for unintended consequences. Chemical reactions in the dust, loss of volatiles to space, feedbacks we did not predict. Terraforming in this phase is as much about restraint as it is about ambition. Phase 3. Pressure increases and water flows, 2,200 to 2,400. If the warming succeeds, the third phase is where Mars begins to change visibly. As atmospheric pressure climbs above a critical threshold, still far below Earth's, but high enough to matter, hidden water awakens. Ancient river valleys that have been empty for billions of years feel the transient trickle of meltwater flowing again during warm seasons. Briny seeps appear along crater walls, fleeting dark streaks that fade, reappear, wander. Ice sheets buried just below the surface begin to soften, slumping into lowlands and shallow basins. In these depressions, the first stable, though shallow lakes may form, cold, tinted red by suspended dust, capped by seasonal ice. From orbit, dark patches glisten where once there was only rock. Terraforming efforts diversify. Some teams seed black dust or engineered dark microbes across bright polar areas to absorb more sunlight and accelerate melting. Others construct massive dikes and levees, not to protect cities from floods, but to guide scarce meltwater into strategic reservoirs where it can be stored, studied, and slowly turned into the foundation of Martian hydrology. At this stage, humans can still not walk outside without a pressure suit or breathing gear. But the suits are lighter, the risk of instant decompression lower. A fall that once meant certain death might now be survivable. The planet is not yet friendly, but it is slightly less hostile. Centuries pass. Between the 2020s and 2040s, Mars becomes a world of seasonal water, thin clouds, and dust storms that begin to resemble weather rather than pure chaos. Habitats cluster near new lakes and channels. Children grow up who have never known a Mars as empty and dry as the one we first encountered. Phase 4. Biological introduction and spread, 2400s to 3000s plus. Only after the climate has stabilized into this new, somewhat warmer state does the fourth phase truly begin. Biology is invited in. At first, it is microscopic. Engineered microbes are released into carefully chosen test sites. Shallow basins, former lake beds, sheltered craters with favorable temperatures. These organisms are designed not for beauty, but for endurance. They endure cosmic radiation, desiccation, and freezing. They cling to rocks, metabolize minerals, and exhale gases that subtly reshape the air above them. Oxygen, methane, additional greenhouse compounds. Lichens and hardy algae follow, spreading over damp rocks when meltwater is present, going dormant when it vanishes. Over centuries, the dull reds and browns of the landscape begin to pick up faint greens and blacks in certain regions. Not forests, not yet, but films of life. Biology becomes a quiet planetary machine, slowly thickening soils, binding dust, darkening surfaces, and nudging atmospheric chemistry. Each new species introduced is preceded by decades of modeling and contained experiments. A single extremophile run wild could derail delicate chemical balances or outcompete native life, if any still hides in Martian shadows. By the late 2000s and beyond, in a best-case sustained effort, patches of the surface could sustain more complex plants during the warmest seasons. Red or purple photosynthesizers tuned for the dimmer sunlight, low pressure, and unique chemistry. These are not Earth's forests transposed, but alien gardens, grown deliberately to serve both ecology and atmosphere. Terraforming has now become less an engineering project and more a planetary-scale act of gardening, with centuries between planting and harvest. Phase 5. Breathable atmosphere achieved, 3,000 seconds to 5,000 seconds or beyond. The final phase is the most uncertain and the most distant. To reach an atmosphere that humans could breathe without a mask, perhaps thin but survivable, requires not just warming, but the sustained incorporation of oxygen into the air at levels that do not vanish instantly into rocks or escape to space. This is a task measured not in centuries, but in millennia. Biological oxygen production must outpace its consumption by the surface and interior. Artificial methods may assist, vast arrays of atmospheric processors splitting CO2 and water, orbital or ground-based machines building up nitrogen analogues or importing missing gases from elsewhere in the solar system. Magnetic shields at Mars L1 point or in orbit might be deployed to reduce atmospheric loss to the solar wind. If all of these work together, biology, machines, orbital infrastructure, and careful management, some models suggest that between the years 3000 and 5000, select low-lying regions, such as the depths of Hellas Planitia, could reach borderline breathable conditions. You might still want supplemental oxygen, but you would no longer instantly suffocate stepping outside. Even this is optimistic. Any number of factors could delay, accelerate, or entirely prevent this outcome. But as a rough, realistic arc, we are looking not at someone's retirement horizon, but at a timeline that spans more generations than any human story has yet contained. Why rushing might not work? The importance of stability. It is tempting to imagine turning on terraforming like an enormous planetary switch. More mirrors, more factories, more power, more speed. But a planet is not a machine. Its feedbacks are subtle, delayed, and often invisible until they tip. Raise temperatures too fast and you may trigger massive dust storms that block sunlight and undo your warming. Release the wrong mix of gases and you might create a chemically unstable atmosphere that collapses or becomes toxic in ways no simulation predicted. Push water into the wrong basins, and you could accelerate erosion that buries infrastructure under mud and landslides. On Earth, climate systems took millions of years to stabilize into the patterns we now recognize, and even they are fragile. On Mars, every step up the ladder of habitability risks slipping backward if the planet's new state is not allowed to settle, equilibrate, and be understood. In this sense, going slower is not failure. It is control. It keeps the dream from collapsing under its own speed. Alternative faster timelines if breakthroughs occur. Of course, there is another possibility, that somewhere along this timeline we discover something shocking. Perhaps a revolutionary fusion technology makes limitless power cheap and compact, allowing vast atmospheric plants and orbital mirrors orders of magnitude larger than anything we can currently imagine. Perhaps self-replicating nanofactories, seeded in the regolith, build infrastructure autonomously across half the planet, in a single century. Perhaps we learn to engineer microbes so precisely that they act like programmable atmospheric engines, sculpting gases and temperatures with surgical precision. In such a future, the phases compress. What once took 500 years might take 50. Terraforming could, in principle, move from a 10,000-year odyssey to a 1 or 2 millennium venture, or even less in the most optimistic scenarios. And yet, even here, one boundary remains: time itself. Biological systems still need cycles to adapt. Rocks still weather at finite rates. Ice still melts according to the laws of thermodynamics. No matter how advanced our technology, we cannot make a Mars ocean age 1,000 years in a decade, or a young atmosphere learn all its own complex rhythms overnight. The realistic timeline to terraform Mars is therefore a blend of humility and possibility. On the one hand, we accept that without extraordinary breakthroughs, we are talking about thousands of years. On the other, we leave space for the unknown, for discoveries that shorten those spans, that bend planetary time slightly closer to human time. In the end, to ask how long it would really take to terraform Mars is to ask a different question. How long are we willing to think? Not in election cycles, not in lifetimes, but in civilizations. Terraforming is less about changing a planet quickly, and more about choosing to be present for a story that will not finish for many ages to come. Before we imagine a whole planet turning green, we should pause and consider something far closer at hand. Perhaps the first truly livable Mars will not be a world transformed, but an archipelago of tiny artificial Earths scattered across a red horizon. Paraterraforming is the art of building worlds inside a world. Instead of changing Mars itself, we wrap pieces of it in glass, metal, and magnetic fields. We create envelopes of air and warmth where none exist, bubbles of habitability that float in an ocean of dust and cold. Picture the first one. A vast transparent dome rises out of the Martian regolith, a curve of glass and composite so large it swallows an entire crater. Inside, the dull red of Mars softens to browns and greens. The air is thick enough to breathe. Frost patterns form on the dome's inner skin at night, then melt with the pale morning light. Beyond the curve of the structure, the sky is still thin, still hostile. But under the dome, the wind has a ceiling. The horizon has walls. Domed cities are the most iconic expression of paraterraforming. They are, in essence, local atmospheres manufactured to order. Pressure, temperature, humidity, even the color of the sky can be tuned. On Mars, where the outside pressure is less than 1% of Earth's and the average temperature could shatter steel with cold over time, this control is not a luxury. It is survival made visible. The engineering is immense but not unimaginable. Materials strong enough to hold in an atmosphere, layered with radiation shielding, smart glass to filter harsh ultraviolet, built atop anchors drilled deep into bedrock to withstand dust storms that can swallow the planet. Inside, gravity is still Martian, but everything else, from the sound of footsteps to the smell of damp soil, is stolen directly from home. Yet not all Martian life would live under the sky. Beneath the surface, another kind of city takes shape. Tunnels snake through ancient lava tubes, natural caverns carved by rivers of molten rock billions of years ago. Here, the rock itself is a shield, blocking cosmic rays and solar storms far more efficiently than any dome. Ice deposits rest in the walls, waiting to be melted into drinking water, into air, into rocket fuel. Underground colonies are the quiet, hidden face of paraterraforming. Corridors branch like roots, leading to pressurized chambers, farms lit by artificial suns, workshops, and sleeping quarters where the hum of ventilation replaces the whisper of wind. Over time, these tunnels could link craters to canyons, small bases to sprawling subsurface metropolises, forming a planetary nervous system of pressurized passageways. Imagine stepping from a train that has traveled for hundreds of kilometers entirely underground. You disembark into a cavern so vast it has clouds of its own breath, condensed in the cool air high above. Somewhere far overhead, on the surface, a dust storm rages. Down here, it's a rumor, a weather report, nothing more. Connect these underground arteries to domed surface hubs, and you begin to see what paraterraforming really offers. Not a single unified project to reshape an entire planet, but a tapestry of habitats stitched together over time. 1,000 small Earths growing, merging, expanding, until much of Mars is threaded with life, without ever needing to change Mars as a whole. The most powerful difference between this approach and full terraforming is not just scale, it is time. Full atmospheric terraforming, the kind that lets you walk outside in a light jacket and take off your helmet, demands centuries, likely millennia. Each step is slow and planetary. Gases must build up, oceans must melt, magnetospheres must be conjured or replaced. Every feedback loop moves on geologic time. Paraterraforming moves on human time. The first inflatable habitat could arrive with the first crewed mission. The first buried base could be carved within a decade. Within a single human lifetime, entire domed districts could be built where children grow up never having set foot on unpressurized soil. Not because we rushed, but because local engineering scales differently than climate engineering. Instead of waiting 500 years for Mars to grow a thicker atmosphere, we build it one room at a time. In timelines, this distinction is profound. A paraterraformed Mars could support thousands, then tens of thousands, perhaps millions of people, while the sky outside remains thin and lethal. Our descendants might retire, have grandchildren, and live full lives on a world that is, outside the nearest airlock, still frozen and airless. For them, Mars would be livable, even if Mars itself is not yet alive. But livable is not the same as free. Life in enclosed habitats comes with its own gravity, even under Martian skies. Air is recycled and measured. Water is accounted for in decimals. Every plant, every pet, every extra kilogram of mass must be justified within the tight bookkeeping of closed systems. Quality of life becomes a question of design as much as engineering. Does the dome have trees tall enough to get lost beneath? Is there room to run, to play ball, to build rivers purely for beauty and not for function? Does the underground city have gardens that mimic seasons, not because they're needed for food, but because human minds evolved with autumn? In a fully terraformed Mars, at least in theory, you could walk for days across open land, feeling the chill in your lungs, watching clouds gather on distant volcanoes. Under paraterraforming, you pace the length of corridors and plazas, parks and cavernous greenhouses. Large, yes, but finite, defined. Yet containment has its own comfort. Pressure control means storms can never strip your air away. Temperature control means crops do not fail because of a rogue dust cloud. Local magnetospheres, built into domes or buried coils deep underground, can shield specific habitats far more easily than a whole planet. A domed city can be tuned, adjusted, repaired. A failed climate on an entire world is far harder to reset. This raises a quiet, unsettling possibility. Perhaps full terraforming is not necessary at all. If we can build vast, energy-efficient enclosed ecologies, if we can make cities and cavern networks so rich and varied that they feel as spacious as countries, then why reshape an entire planet? From a resource perspective, paraterraforming is less wasteful. From a risk perspective, it is more contained. From a technological perspective, it is achievable with tools we can realistically foresee over the next century. And so another question emerges, one not about engineering, but about ethics and identity. Should we terraform Mars at all? Transforming a planet is not just a project, it is a statement. It says that this world, with its ancient valleys and dried river deltas, its minerals and silent horizons, is raw material to be moulded into our comfort. Some argue that this is an extension of life's natural impulse, to spread, to adapt, to transform its environment as forests and reefs have always done. In that view, making Mars blue and green is not hubris, it is continuity. Others look at the rusted plains and see a museum older than any civilization, a record of planetary evolution frozen billions of years ago. To flood those canyons with water, to breathe nitrogen and oxygen where once only carbon dioxide drifted, is to overwrite a story we barely understand. If we discover microbial life deep underground, does that change the equation? Does Mars become a sanctuary we steward, not a canvas we repaint? Paraterraforming sits uneasily in the middle of this debate. By confining our habitats to domes, tunnels, and enclosed valleys, we leave most of the planet untouched. For a while. We create islands of Earth amid an alien sea, preserving the wider environment, even as we learn to live within it. It is a compromise, an experiment. It lets us ask, in practice, rather than in theory, how much of Mars do we need to change for Mars to feel like home? Centuries from now, those future Martians may stand beneath the arch of a crystal dome, looking out at an unbreathable sky. Behind them, children play under artificial clouds and LED suns. Ahead of them, the raw planet stretches into the distance, cold and red and ancient. They will be the ones to decide. Do they break the dome, step outside into a world they have warmed and thickened, ready to embrace them? Or do they keep living inside their constructed havens, content with a Mars that is partly tamed, partly wild? Our role, here and now, is not to know the answer, but to understand the options. Full terraforming is a saga measured in epochs. Paraterraforming is a chapter we could begin to write within a single lifetime. Somewhere between the two lies the future shape of Mars, a future in which time, technology, and philosophy all converge to decide not just how long it would take to terraform a planet, but whether we ever truly should. We began with a simple question. How long would it really take to turn Mars into a world that feels, even vaguely, like home? After all the numbers, all the engineering, all the biological speculation, the answer is not comforting in the way a countdown usually is. Depending on what we mean by terraformed, the timeline stretches from 500 years for a barely breathable, marginally warmed Mars, to 5,000 years or more for oceans, forests, and skies that could be mistaken, at a glance, for an alien echo of Earth. On human timescales, that feels almost impossible. On planetary timescales, it is the blink of an eye. And yet, the vastness of that timeline is precisely what makes the project meaningful. Terraforming Mars is not a single mission, or even a single civilization's achievement. It is a relay across generations. Each century passes the baton to the next. The engineers who build the first sealed habitats, the miners who redirect the first icy asteroids, the biologists who craft microbes that can cling to frozen regolith and slowly, silently exhale oxygen into a thin red sky. Why pursue a dream that no one alive today will see completed? Because the act of beginning reshapes who we are. The first sealed greenhouses on Mars, the first underground cities protected from radiation, the first genetically tuned lichens clinging to basalt. These are not previews of some distant future. They are the future, unfolding in slow motion. Each step will teach us how to live in harsh environments, recycle every atom, and treat atmospheres and ecosystems as precious fragile systems to be maintained, not consumed. In that sense, Mars does more than promise a second home. It changes how we look at the first one. Once we learn how hard it is to build an atmosphere from scratch, a thin blue sky over Earth will never feel ordinary again. The first steps are not science fiction. We can take them now. Better robotic explorers, in situ resource utilization, nuclear and solar power grids designed for dust and darkness, precision life support systems, closed-loop habitats on Earth and in orbit that rehearse Martian life before anyone sets foot there. Each of these is a brick in a cathedral, whose completion date is unknown, but whose foundations must be laid deliberately, and soon. If we choose this path, space colonization stops being a series of isolated flags and footprints, and becomes an intergenerational craft. The question shifts from, can we get there, to, what kind of ancestors do we want to be? A multiplanetary species is not defined by rockets alone, but by its willingness to start work on futures it will never personally inhabit. If you've stayed with this journey, through dust storms, orbital mirrors, magnetic shields, and microbial pioneers, take a moment before sleep to imagine that distant Martian dawn, a sky no longer black, but a faint scattered blue, frost melting into streams that carve old crater walls, a child looking up at a small, bright star in the sky and learning that it is not just a star, but the ancient birthplace of their species. If this vision resonated with you, consider gently tapping like, and let us know in the comments where you're listening from on this tiny world. If you'd like to join us as we keep exploring these long, slow stories of the cosmos, you can subscribe and, if you wish, become a channel member to help support what we do. Completely optional, always appreciated. For now, let your thoughts drift across the gulf between worlds and rest in the knowledge that some dreams are so large, they are meant to be shared across centuries.